So in regular physics, we have them not do this because there's a lot of math to this. So instead, what we have them do is I think we still have them find the focal length. Do we have to do that, or do we? I don't remember. It's been 6 months. Anyhow.
Yeah, we do. Sometimes we put a light far, far away and have them focus that and tell them if that's the focal point. Actually, I think we have them find 2F now.
Yes.
It's just easier to do with their lab table. They find the place where the object and image. Now, for you and I, it would be easy. When we use a candle and a piece of paper, we would move them at the same time together until they match up. But it's amazing. But it's not intuitive that, okay, if they're both going to be at the same point, move them both together. So you can find the 2F point of your mirrors very quickly. We find our mirrors are slightly different too.
Yeah, they're all slightly different.
Yeah, that's why we go through that. So we have them do 2F.
Right. And then, of course, they just divide in half to get into F. And then we break them up into what we call zones. We call that one zone 1. And this is just completely made up. So you're not going to find this in any textbook. Zone 2, zone 3, and zone 4. But each one of those zones has distinct image types. And depending on if you put an object in zone 1, no matter where you put it in zone 1, so from 2F to oblivion, the image is always going to be located in zone 2. It's always going to be smaller, and it's always going to be upside down.
Why don't you draw this? Let's draw pink and pink.
So get out your pink marker.
And then what I tell them, because all light paths are reversible, well, couldn't this just be the object? The light rays would go backwards, making this the image. So if you really know 1, the object's in 1, the image is in 2. You really know the other way around. The object is in 2, the image is in 1.
Right.
Larger, and the other direction, upside down. Okay. We don't use the terms. We're being
Oh yeah. We don't use the textbook terms.
Inverted and not inverted.
Right. We also, something I was going to say.
1 to 3.
The real. Then we also tell them these objects are real, so they're upside down. Hence the coffee. The real coffee was written upside down. Now we obviously don't give our kids coffee, but that's just for you guys, a little added bonus. But then if we put an object in 3, right, the image is in zone 4, and it's larger and it's right side up. And then if you put it in,
right, that works for convex.
You got it. That works for convex.
Zone 4, then it's just the convex side.
Right. So you get the smaller image. You get big bad Brad. Okay. So and it takes all the math out of it. So if you're teaching physics first, or if you're teaching a conceptual physics, there's no math that needs to be done, but it still gets the point across just fine.
Then if we look at the difference, the boundary between the zones, if we move an object, we know that if the object's in 1, the image will be in 2. So if you move the object from 1 to 2, the image has to move from 2 to 1. Well, where's the point that they meet? It must be right at 2F. It's the boundary between the zones. How about between 3 and 4? Right at the rear. Yeah, right at the surface. If you put you want to take your concave and convex out?
I don't know what you're talking about.
The mirrors? But the image size, and the image size were either...
Yeah. The little guys?
No, the regular ones. But the image size turns to be the same too. What you find is when they meet, the object and image are the same size and the same distance from the mirror. Same thing will happen here when you're right up there. Put your hand right there. Yeah, isn't the image the same size? Other side too, on the convex side. Yep. Put your finger right there, the tip of the finger. So it works the same. So at the boundaries, we get same size images, but because this is real, we'll have it upside down. Here, right at the boundary between those zones.
And of course, the farther you move that object in zone 4, the farther you move it away, the closer the image is going to come to the focal point, right? So therefore, if you put an object at the focal point, the image has to be at infinity, right? So it's just, which is another impossible concept for students to understand.
Yeah, I was just going to say real quick, if you go from 2 to 3, what do you talk about?
I say that F stands for the flipping point. Right, so there's no, it is the focal point, but that's the flipping point, because F is the boundary between real and virtual, so between upside down and right side up.
Yeah, so it's pure memorization here, we're not really teaching them anything. However, when we want them to learn about applications of mirrors, it's helpful to talk about the zones.
So 1 and 2 are real, 3 and 4 virtual, and in between is the never, never.
Yeah, never learn them, yeah. And I tell the regular kids, both kids, that in our class, we're never gonna have an image at the focal point. So we can get light come through there, but for seeing images and looking at images, we're never gonna get one at the focal point. Yep, and by the way, those equations, SO, SI, or SISO equals F squared, work for both concave and convex. All you have to do is take a look at what values are negative. If it's from the focal point onward, your SO and SI are positive. If anything is from the focal point to the right, they're negative values.
Again, I don't know if I'm going in order here, because I just figured this would be a good time for this.
Good time for this?
Just one. Just take one and pass the rest back. Now these are super cheap mirrors. They're but concave. Did you go okay? Well, who said this is yours? This is mine. But here you can, you can hand these out to students if you buy a class set of them, which they're not expensive. I think for 24 they're
They're
$6, $10 for 24 maybe.
I think they come in packs of 10.
Where do you get them?
Yeah.
Yes. I'll tell you. in a minute,
Arbor or
okay?
Sergeant Plum.
Yeah, one of those.
But you can put the object, your head, in zone 1. So you hold if you hold the concave side towards you, and you hold it far away, you'll see a small and upside down image, right? And then as you bring it in, you'll see that your image stays upside down, but it gets bigger and bigger and bigger and bigger, right? Until eventually, if you bring it in far enough, like right up to your nose maybe, or up to your eye, you'll see a giant eye, right? Or a giant nose. Right, or both.
Yeah.
Exactly, see every pore. With students, it's wonderful. I said, this is the Pimple Popper 2000. I mean, but then if you hold it far away from yourself with the convex side towards you, no matter where you put it, you're always smaller and right side up. Right? Then if you turn it, now this is just an added bonus, and this is again something for the last 30 seconds of class. If you hold it towards yourself, put the concave side towards yourself, I always do this because somewhere along in my education, like in 3rd, 4th, 5th grade, my teacher taught me that a bear digs out a cave, so it's concave, and I teach them that. And my students are like, that's the stupidest thing in the world. And every time on the test, I see them, but if you then take your finger and touch the back of your face, touch on the back, right about where your face is. Now open your mouth up wide, and then push in a little bit. A little mini you comes growing out of your mouth. So there again, again, one of those ones you want to do at the very end.